Hi, good morning, everyone. So, in the last class, we derived the learning rule for MLP. We discussed the merits of the MLP and just about discussed the demerits of this model. So, one of the big complaints about MLP for a long time is that it's like works like a black box, right? So you have the network, which is inside this box. Input goes in, output goes out. Uh, so we don't know what's happening inside. That's a big objection. So, so with the advent of deep neural networks, actually it's become worse because networks got bigger and they're said to be conceptually opaque. That is, we don't know what happens inside. It's just that we're assured of performance because it's been tested on a lot of data, right? And that's a big weakness. In the early days of neural network, people used to actually go into the network and probe the hidden layers and see what the neurons are up to. So, for example, I'll show a couple of examples of that kind later. But these days it's not common, so that objection is still valid to some extent. But we'll see later on in tomorrow's class that people have compared the hidden layer responses of a deep neural network with the response of different areas in the brain when the network is trained on a visual pattern recognition problem. And they found that there is a very nice correlation between the layers of the visual hierarchy in the brain and the different hidden layers of the deep neural network. So it's not that bad. I mean, it's doing something logical, and so if you probe it with the right tools, the right methods, you'll see some logic in what the network is doing. So limits of generalization is not clear. It's a very big problem. In fact, whenever we see news that some driverless car has got into an accident and killed somebody, that's an example of how the network is generalized, has generalized into to a pattern which is not appropriate. Right. So this is a very deep problem, and since it's a highly nonlinear model, it's very hard to find out what the limits of generalization. So we'll talk a little bit about that also soon. Hard to incorporate prior knowledge of the model. That is, I gave an example last time. Suppose I'm recognizing alphabets, right, A, B, C, D, and so the recognition system must be translation invariant. That is, no matter where I present the letter in the input frame, I should give the same result. Right. Secondly, no matter what the size of the character is, it should give the same result. So the network should be translation invariant and scale invariant. But there is no obvious way of incorporating it into the network weights by hand. Right. You just have to present it lots of characters at different places in the input frame or characters of different sizes and train it to recognize in the same way. So there is no simple way of doing that. The net training is slow because usually training is done on all the data, and it's a slow process. But the thing is, once it is trained, it's fast, so there's no problem. Another thing is it has a problem of local minima. That is, that the network is trying to minimize as an output error cost function to find the optimal weights, and the cost function can be highly nonlinear, as you see in this picture, right? E, if you plot this error E as a function of some weight variable or weight parameter, right? There can be many minima in it. So since the network is doing gradient descent, it will start from some point and then just kind of slip into the nearest minimum. So this is called local minimum. That minimum doesn't need not have to be a very deep minimum. So only when you actually start from the neighborhood of a deep minimum or a global minimum, you will find a global minimum. Right. So this is also it is sensitively dependent on the initial condition, and you have no control over the initial condition because you set it randomly. But one good news here, which ameliorates this problem, is that there are large number of solutions, equivalent solutions. Right? For example, if I take a MLP with one hidden layer, and let us say the hidden layer has n neurons, right? And think of this as a physical network where the hidden neurons are some kind of, beads, right, or spheres, and the weights are some connections are some kind of threads. So now, if you just permute the hidden layer, these spheres, right? And the threads also move along with the spheres. Then it's still the same network. Physically, it's still the same network. But that permutation means, mathematically speaking, it's a different network because now the weight pattern has changed, right? And So which means for all the permutations of the hidden layer, if you are moving the weights also along with the hidden neurons, right, correspond to the same network. That means for any given network with a given weight pattern, there are n factorial minus 1 other equivalent networks which have identical input-output relationship, right? Which means that if I have a part of a given region in the error landscape, which has some error, right, some low error, there will be about n factorial, right, networks, that many networks, which have the same error. So basically what that means is the error landscape is quite rich. There are lots of local minima, right? So you are likely to hit one or other. Okay, so it's not too bad. And especially when you take a larger network and take precautions about generalization and all that, you will generally hit a good minimum. So now how do you develop a network, right? First thing is you need to do a feasibility study. This is more relevant for an artificial network development, but anyway, I'll just quickly summarize this. Then you have to collect some training data, and but then you train the network, then you test the network and deploy the network. So I'll skip this. You need to have a lot of domain knowledge to train the network well, and you should know how to break up the problem. Sometimes breaking up the right, training a big network on the entire problem may not be a good idea. You want to break up the problem into smaller problems and train separate networks on different problems. So because data is very important, because what you're doing here is uh, put the training data in a more active form. Training data simply has pairs of x and y vectors. All right, you're putting it in active form, which is a neural network, in such a way that if you give x as input, it returns y as output. It also generalizes to other patterns which are not there in the training set. Now, we want to pre-process the data. That is how you pose the problem to the network, right? How do you represent the problem to the network? Also can be quite critical. Sometimes a bad representation can make the training problem very hard. And same thing, if you change the presentation slightly, it can become very easy. Let me give a small example. Suppose I want to classify numbers into odd or even numbers, and I want to train a neural network on that. So it's a two-class problem. Now, if you represent this number in decimal form, like let's say 327 in decimal form, I can think of some representation. Right? Let us say I have only 3-digit numbers, and since I have 10 digits, I'll have 10 neurons for each digit. So I'll have, let's say, 30 neurons, and train the network. So it can be quite a hard problem to classify the patterns into even or odd. But now same thing I convert into binary form, right? And so I have a huge binary vector. Although it's a much longer representation than the decimal, you see that odd even classification problem becomes trivial if the input data is binary, has binary representation. So just by looking at the first bit, the 0th bit, I can make out whether it's odd or even. So I can even set the weights by hand. I don't care about all the other bits. I just set all the other weights to 0. Right? I only set the weights weight of the. I can solve this using a single neuron. I don't even need an MLP. It becomes so. What is so difficult with one representation becomes trivial in another representation. Representation can be quite important. Then the second thing is there is a need to reduce input dimension, because as input dimension is higher and is grows, right? The requirement on the amount of training data that you have also grows exponentially. So see, for example, if I have let's say one-dimensional data, and I say that with, let's say, without loss of generality, the data is confined to unit interval. Now let us say I want to take 10 points in the unit interval at uniform sampling. Then same thing, if I take 2D data, then it becomes 10 times 10. We'll have grid of 10 by 10 grid. Then that's 100 points and so on. So as my input dimension grows, the number of points I would need to represent the input space uniformly would grow exponentially with the dimensionality. So we'll have 10 power n for n dimensions. So if your sampling is a points per unit interval, then it's a power n. So basically it grows exponentially as input dimension. So there you need to try to reduce the input dimensionality. There are many ways of doing it, like principal component analysis and feature extraction, all that. So then next we talk about architecture, initialization, and training. Architecture, in this case, we are talking about only MLP. So, which is, you can also say it's a deep network, the same thing, mathematically speaking. So, do you want to have one hidden layer, two hidden layers, and so on and so forth? So, although the theory, mathematical theory says that one hidden layer is good enough, as long as you have the enough number of hidden neurons in the hidden layer. In practice, it is good to have multiple hidden layers because what happens is if you have multiple hidden layers, typically the lower hidden layers tend to represent some local simple features, and as you go to higher hidden layers, they tend to represent more global features. Especially, this is the kind of thing that happens in a particular kind of network called convolutional neural network. We'll talk about that very soon. So suppose you train a network like this on face recognition, recognizing faces. So what can happen is lower layers might just be responding to small oriented lines. Okay, middle layers can respond to eyes and mouth, things like that. Higher layers can respond to whole faces. So this kind of hierarchy will automatically emerge if you have large number of hidden layers. The advantage of that is, right, if I want to suppose I have a network trained on one set of faces, and if I want to use the same network and train it on a different set of faces, let us say these are one red network is trained on Indian faces, and now I want to move it and find develop a similar network for Caucasians. I can start with the same network. Maybe I can cut out some of the lower layers of this network and move it here, right? And initialize the lower layers of the new network using the lower layers of the previous network and train it, and it will work. It will speed up training of the new network. That kind of thing is possible because there is an intrinsic hierarchy in the first network, and which is possible because there are lots of hidden layers. So using hidden layers, number of hidden layers is a good policy, but you need to should not overdo it. You need to know what is the optimal number of hidden layers, which is again done by trial and error. Okay, then sometimes you want to use customized architectures, especially if you are developing network models for brain function, like in computational neuroscience. You may sometimes want to constrain the network architecture by your knowledge of real brain anatomy. Okay, so for example, if you are modeling visual system, right? So you have input from retina to LGN, and there's V1 and V2. Okay, so thing is there's feedback from V1 to LGN. I cannot just feed forward. And similarly, there's feedback from V2 to V1, not just feed forward. So these kinds of anatomical features from the brain, which will have to be incorporated into the model if you want to get a sufficiently faithful model. So that is one thing. Secondly, suppose I want to train a network which will look at some visual input and move some arms to reach to a target. So here is a target. This target is seen by two eyes, right? And two retinal images capture the target at two different points. Oops. Excuse me. So at 2 points, then these two images are given as inputs to a network, and network drives two arms, the muscles of two arms, to reach the target. Now, if you want this model to look a little bit like the brain network, then you want to divide the network into two halves, the left half and the right half, analogous to the two hemispheres of the brain, right? But then the two hemispheres have some kind of a level of connectivity between them, which is given by a big bundle of fibers called the corpus callosum. There's another bundle of fibers which connect to hemispheres called the anterior commissure. All right, so if you want to come up with a model which is basically an MLP but sufficiently realistic in anatomical terms, you want to introduce all these constraints. How do you divide it right in the middle in such a way that it will reflect the two hemispheres of the brain? So that's an interesting problem. So like that, depending upon your brain constraints, right, or anatomical details, you may want to constrain the architecture appropriately. Then you come to training. You can train it using backprop. We already seen it's an algorithm. The backprop is generally it's a bit slow, but there are lots of ways of speeding it up. And that's a huge topic in itself, and I'm not going to spend much time on it. Your learning rate can be adaptive. Suppose initially you start with a high learning rate, and as you approach a minimum, you slow down, right, and decrease learning rate. Or there's something called momentum, and you can use that to speed up learning. There are also higher order methods. I'll talk about that in a minute. Also, when to stop training, there is the simplest way to stop training is when the error goes less than some required threshold, let's say epsilon 1. Sometimes what happens is the error goes down initially rapidly and flattens out at a very high level. So then you don't want to wait until this first condition is satisfied, because that might never be satisfied. So then you make sure you use a slightly more a weaker condition. That is, when delta is less than some threshold, you stop. That is, when it is sufficiently flat, you stop. Okay, so another way of stopping is what is called early stopping, where you look at the performance both on training data and also a separate actually validation data set. So what happens is when you train the network on a training data set, the error keeps going down on the training test data set. But if you use separate validation data set, there also error initially. So usually validation data set, since it is different from the training data set, error will be higher, but and it will keep decreasing with training time. But what will happen is, while the training error keeps on decreasing monotonically, that's a typical behavior. The validation error will go down up to a point. After that, it will start increasing. So this is where you want to stop, because beyond that, you'll see that the network will not generalize well. Okay, so this is a good point to stop training. So this is called, this kind of training, this kind of stopping criterion is called early stopping. So like I said, there are higher order methods. So in backlog is a first order method. That is, the weight update depends only on the first derivative of the error. There are also higher order methods which depend on second derivative. That is, you have to calculate Hessian, dou square E by dou Wi dou W, dou Wi dou Wj. Okay, there can be, I mean, the computation look intensive, but the number of steps can be smaller. You can might be able to jump to the solution much faster. So, but from a physical point of view, again, it's slightly more difficult to justify it. But anyway, then comes to generalization. So the problem of generalization can be explained like this using a Venn diagram. So basically, what the network is doing is it's taking some training data set and is trying to model a function. So in this picture, the overall rectangle is the universal set U. Okay, which denotes all possible input-output pairs. All right, the universe of input-output pairs. Within that, there is a subset called F, which represents some function. So this is a set of all input-output pairs which denote that function completely. Now we don't have access to that function explicitly, so we take a bunch of input-output samples which are thought to represent that function. But since right, this set of samples, which is training set, can only underrepresent that function, because you can never cover the function completely, because you need infinite samples to do that. So I'm representing it as a subset T, which is a training set. So now what the network does is it suppose it does well on training set, right? So this other strange shaped set represents what the network has learned. So since network is trained on the training set, right, it try to do well. It will capture all those patterns. It try to do well on that, and it will also generalize it in some strange direction. Okay, so thing is, if it does like this, you see that X is the test set. If what the network has done learned is, and or it is, if it is generalizing like this, it will do very well on the training set, but it will do very badly on test set, because it hasn't got any of the test patterns right. This is quite possible. So this is a problem with neural network training, right? So there are many ways of again ameliorating this problem. To give a small illustration of how to deal with this, let us say I have this function y equal to some 4x into 1 minus x, which is a parabola. I want to learn this function, and for this I have a bunch of samples, and the samples also have some noise in it, so the points don't exactly lie on the parabola. So now I train a network to learn this function. Only thing is, since I don't know how complex the function is, I take a large network and kind of literally train it to death. That is, I want it to get all the points right. So since the network is large, it can produce a very complicated plot. It will go through all the points and capture all the points, and maybe get training error is 0. But the point is, when you give new points from the test data set, since the network plot is so complicated, it doesn't look anything like the underlying parabola. It will make a lot of errors on the test data set. The test data set comes with its own noise addition. So whereas, so it's not good to train it on all the data points such a way that the training error is low, right? And in this case, you have taken a network which is too complicated for the problem. So whereas if you look at the second plot, the network is not a very complicated model because it looks quite smooth, doesn't have too many wiggles in it. So the error might be slightly high, the training error, but the test error will be somewhat low compared to the first case. That is, if you apply the early stopping, you will find that both the training. So in this kind of in this situation, so situation A, right? So this is overtraining. You will find that the training error will be very low, but test error is high. Whereas this is not overtraining. Both training error and test error will be quite low. So the trick lies in matching the new network complexity with the problem complexity. Okay, so that is when you get best generalization. And people also do pruning of the way of the network, because so basically the overtraining is possible or occurs likely to occur when the network is very large. Is very large means having too many trainable parameters or free parameters in the network, which is what happens when you have lots of neurons, right? So pruning the network in such a way that the unnecessary weights that don't contribute much to the output error, right, if they are removed. And how do you do that? There are many. Again, this is also a very big subject. I'll just mention 2 examples. One is called weight decay. That is, as you train the weights, make sure they are not very big, right? They're the smallest size possible in magnitude. So how do you do that? In addition to the squared output error, you add another objective function, which is usually an even function of the weights, which will make sure that the weights are the smallest possible. One way is just make this equal to the sum of squares of the weight values. Now, when you do the gradient descent on such an objective function, what you will get is delta wij is equal to eta delta I vj. This is your normal backprop term that you get from gradient descent. In addition, if you do gradient descent on this, you will get some additional term which is proportional to minus wi. Okay, so that is the weight decay term. So it will tend to decay. So this term will keep pumping up the weight if the weight turns out to be important. This term will keep destroying the weight or make Hj, right? It will keep killing the weight, decaying the weight. Finally, only the weights that are sufficiently relevant to the output error will survive. The other more complicated methods called for example, brain damage, where wij is set to 0 only when it is found to be necessary. So that is, so basically you have some W. Initially, you train the network completely. Then you have some weight value. Now you ask the question, what will happen if I just set that weight to 0? Right? What is the change in the error? If the change in error is not much, then that weight is useless. Right? You can remove it. So using such criteria, you prune the network and reduce the number of free parameters, which will improve generalization of the network in the test set. So I will describe now a few applications of MLP which are of interest more in psychology, right? And so I'll be looking at parallels between some psychological phenomenon and the behavioral phenomenon and the performance of a neural network. and show the parallels. So I'm only looking at behavioral aspects right now. But in the next class, I will also try to convince you that not only at behavioral level, even at level of activation, a simple deep network can show you very interesting parallels between brain's activity patterns as the subjects perform some sensory processing task. Right. So let us see this some examples today, and we'll look at more tomorrow. Um, so the first problem is what is called past tense learning, and so learning past tense when kids learn English, right, English grammar, learning past tense is an interesting problem. And apparently, kids when they learn this, they learn this in 3 stages. In stage one, only a small number of words are used correctly in past tense, because in stage one, as you look at very young kids, their vocabulary is also small, so they know certain commonly used verbs, and they know those verbs in both present tense and past tense. So typical examples that the kids are familiar with at a very early stage is come, came, get, got, give, gave, and things like that. So they get all these past tenses right. So the thing is, past tense in English is a bit of a challenge because there are two categories. There are these regular verbs and irregular verbs. If you look at regular verbs, then typically the past tense is obtained by adding either a D or an ED at the end. All right. Irregular verbs don't have any such pattern. You just have to memorize the past tense. So learning past tense means knowing which to use when. So that means you should know that if a given verb is a regular verb, you should just add an ed at the end. Or if it's not a regular verb, you should know and should have memorized what is the correct past tense form. Right. So this is a big challenge in learning past tense of verbs. So in stage two, kids expand their vocabulary, learn more verbs, right? And a lot of verbs are so the regular verbs, so there's no problem. But in stage two, a lot of kids exhibit a curious phenomenon. In this stage, they start applying this regularization rule, if you can call it, to even irregular verbs, and start making mistakes in past tense. Because, for example, in stage one, they are used to the verb come and came, right, present in past tenses, and they get the past tense form right. But in stage two, they understand that there are a lot of verbs that take the standard regular ending, which is ed ending, and start applying it wrongly to even the irregular ones. For example, for come, they might say comed or came, so that they mess up their past tense in stage two. In stage three, they further expand their vocabulary, and so there are lots of regulars and a lot of irregulars also. So by this time, they would have learned to resolve this conflict, right? And they know how to use the correct regular form for the regular verbs, and also they know how to apply the regular form to the new words of the regular verbs. So all these behavioral patterns, which are seen in children, can even be exhibited and can even be reproduced in a small neural network. So earlier, when psychologists studied this phenomenon, they were coming up with very complicated explanations as to why kids do it. But once with the advent of neural networks, they were able to notice that even a simple neural network can show the same behavioral patterns. So how did they do this study? So they have taken this different sets of verbs, 10 high frequency verbs, 8 irregular and 2 regular. This represents the kind of first stage. Then medium frequency verbs, 410 of them, and 333 of them are regular and 76 are irregular. And 86 low frequency verbs, 76 regular and 14 irregular. So using these words, the simple network, actually it's not even an MLP, it's a perceptron. So it's just basically a matrix. Right? It is trained in 3 stages. In first stage, they trained the network on 10 epochs of high frequency verbs. That is the first set of verbs. So you see that the verbs are given there: came, get, give, take, go, have, feel, look, live. Then in second stage, it is 4 and 10 medium frequency verbs are added to this first set of 10 verbs, right? And then the network is trained for 190 more epochs, totally 200 epochs. So in the beginning of the second stage, the network suddenly starts making mistakes and starts messing up the past tense forms of the verbs it has learned already in stage 1, just like how kids do it. Then in stage 3, they just test the network on 86 low frequency verbs, and in this stage, the network is able to learn uh, the, the forms correctly. It was able to give the irregular ending to the irregular verbs, regular ending to regular verbs, giving almost 100% accuracy. So if you look at the error pattern, right, for the first 10 epochs, it's trained on the irregulars, right? And once the second set of verbs are presented, both regulars and irregulars, you see that it starts making mistakes. So error suddenly starts dipping, right? Starts making more mistakes even on the first set of words. And after that, slowly it starts picking up again. After 200 epochs, it got very high accuracy, right? And after that, when it is tested on the 86 low frequency verbs, then it does well even on those words. Next, I want to introduce the convolutional neural network, because this is a network that's applied to for a comparative analysis of brain activation patterns when the subjects are performing some sensory classification tasks. So, convolutional network was not developed post deep learning revolution. It's actually a very old model. It was kind of rediscovered or repopularized in the deep learning era. So this model was first proposed by Lacoon and others. And the first model, I think, was published in 1898 or something like that. This was originally developed to read handwritten digits. This is done as a project for AT&T to read PIN codes or zip codes on US postal envelopes. So a network looks like this. So in the input is an image. I think a lot of you might have been familiar with convolutional neural network. Input is an image. So in MLP, each hidden layer has a 1D layer of neurons. In this case, there are these convolutional layers where each layer has multiple two-dimensional arrays of neurons, right? And a given neuron in a two-dimensional array is connected not to the entire previous layer, but only a small window of the previous layer, right? And then the neuron at the corresponding location in the other, these are called the feature maps, other feature maps, also connected to the same window of neurons, right? So it will be something like this. So it has a pretty peculiar architecture. Now this kind of thing goes on for a few layers. After that, you have one-dimensional layers of neurons, which are called fully connected layers. Um, so you present your input image here, and then so if you are recognizing digits, and present your image here, and output you have 10 neurons. Depending upon the number of neurons, you can find out what's the class of the input image. Thing is, once the network is trained on lots of data, so this is a well-known data set called MNIST data set. So it was tested on some what the website calls weirdos. So just take a look at this website. It's called the Lenet, right? And so the original training data had normal digits like 2 and 4 and all. But just to see push the network a little bit and see how well it can generalize, they synthesize some complicated input patterns. Just to see if network can recognize it. So 2 was synthesized like this with lots of rings. It was able to recognize it. And 4 was given as a hollow 4, this, right, not a solid 4. And 6 was given like this with lots of breaks in the contour. It was able to recognize all of them and generalize well, almost like a human being. The way human being would generalize it and see the pattern 2 in this, although it is a very complicated, kind of internal architecture. Similarly, 3 was synthesized like this with lots of short lines, 5 like this, and so on. It's able to recognize all that. This was a very big, event way back in the late 90s when people were still just trying basic neural networks on problems like this. Okay, so we'll look at a couple of applications of convolutional network. That is applications in computational neuroscience. This is still in artificial neural networks. Right. Next application I will mention is what's called a net talk, the network that is trained to read text and convert it into speech. So converting English to speech, English text to speech is a bit challenging. I mean, comparatively, doing it for Indian languages is somewhat more easy, because in case of Indian languages, what you see is what you read. There's not much of context dependence, right? You may only have to worry about stress and things like that. But in English, the pronunciation of a character depends upon its context. The same character is pronounced differently in different places. For example, this character C can be pronounced as K in cat and S as in facade, right? So there are all these contextual problems. So therefore, it's a bit challenging. And in this study, which was published in I think late 80s, 86, right? The network is trying to convert text into speech, and to that end, they give text as they give window of text as input to the network. So a window of 7 characters are given at any given time. Suppose I want to recognize the sound of this letter S. So since this is this last letter in the word this, right? I give 3 characters before it and 3 characters after that. So I give my window is up to this point. All right, and the output is something like this sound sir, right? And this window is given as input to a network, and output is a bunch of phoneme classes. A network maps this window of characters into some phoneme classes. Since there are 26 characters in English, and there are also some punctuation like commas and full stops, right? Space, comma, and full stop, right? With all this, you have 29 characters. So at each position, I can have 29 possible symbols, right? And so you represent each symbol by binary vector, where depending upon what that symbol is, that corresponding bit is on, all other bits are off. It's called a one-hot representation. So you take that representation for each column, and then you have rows of, there are 7 such columns. And so that matrix is given as input to the network. And there are 80 hidden neurons and 26 output neurons representing 26 phonemes. And why is the window of 7 taken? Because what they found is that the context dependency, right? They've seen to what extent the one character can influence the pronunciation of a neighboring character. What is the domain of influence? So that they measured using a measure called mutual information. That is, right, what is mutual information of between 2 characters that are close to each other? So they found that that is with what probability can you predict a neighboring character, right? Given the information of identity of the character at a given position. They found that mutual information falls rapidly beyond 3. So that means a character does not have much influence over another character which is more than 3 positions away. So therefore, they have taken a window of size 7. Then they took some training data, basic words, and pronounced by some individual. So trained network, and it showed some 95% performance on about 50,000 words. They also found that having hidden layer is quite important. Without hidden layer, that is 0 hidden neurons, the network performance could not rise very high. So now what is interesting is, because it's not an artificial neural network kind of a task, so we're not just interested in performance. We want to see to what extent does it emulate the behavior or the performance of real humans? So one of the first things that they found is that the network is able to distinguish between vowels and consonants. That is, like I was saying, in the early days, people used to go into the network and see what the hidden neurons are doing. So they found that the hidden neurons are able to classify between vowels and consonants, right, very early on. So I think that is interesting because in the training data we have never told the network that there is these two sets of sounds called vowels and consonants. Because all that was given to the network is a bunch of text strings and the corresponding phonemes, right? The vowel and consonant concept was never introduced to the network. But so during the training, it turns out that the network must have found it convenient to classify the input stimuli into vowels and consonants, right? That it has learned that pattern, naturally. And so during training, in the early stages of training, the network has just learned to pause at word boundaries, because after every word there's a blank space. So network also learned to pause, right? But otherwise it was just, there was just babble for the word, but between two adjacent words it learned to pause. And so after 10 passes, 10 epochs, the network speech produced by the network was quite intelligible. And it made errors, but even the errors were quite meaningful. So for example, thesis was pronounced as these, which is quite reasonable. And network really confused between vowels and consonants. So within vowels it made mistakes, got confused. Within consonant it made mistakes, but it really confused between vowels and consonants. And what is interesting is some errors were actually errors due to annotation. That means there were mistakes in the training data set labels. Right, so the network did not make a mistake. There was problems with the labels in the training set. So that was why the network looked as if it did some mistake. Then test performance, we have 439 words from regular speech. Performance was 78%, not great, especially from modern point of view. But at that time, it was I think a good performance. So another thing is damage testing. That is, once you train a network and if you damage it, how well, what is the effect of the damage on the performance? So they just have taken all the weights and added some noise in the range of -0.5 to 0.5. Looked at the performance as a function of the noise amplitude. So up to some point, they found that there is hardly any change. So it was quite flat up to some point. After that, started dipping. So which shows that the network is robust, right, to noise, because there are lots of redundant weights, and because of that, even if you add some noise, the network is able to give good performance. The next thing is what happens when you retrain the network after damage. So once the network right, so the thing is when you take the network, right, this kind of a damaged network where you add noise at a point where its performance is 67%, because the highest performance that it got was 95%. Now you add some noise, and let us say it got, and you take this point somewhere there, where the performance is 67%. From that point onwards, you now again retrain the network. So something interesting was observed. The original training was slow. That is, from 67 onwards, it was risen slowly to reach 95 after a long time. But when we took a damaged network, that is a trained network which is damaged, that is noise is added, and although it starts on the same poor performance, after retraining it has learned faster and reached the same high performance much faster. Now, this is reminiscent of what happens in stroke patients. With stroke patients, the part of the brain is damaged because of loss of blood supply. Right. So right after the accident, you might see that the patient is not able to walk, is not able to speak, lost memory and things like that. but in a lot of patients, they quickly recover, and in more positive cases, hopeful cases, after even a couple of weeks. I mean, I've just seen a friend of mine, his father had a stroke, right? Initially he couldn't walk, but after a couple of weeks he's able to walk, right? Now compare that with what happens in an infant, right? How long does an infant take to walk? I mean, it takes year or two to be able to walk from right from start, from beginning, right? So relearning is much faster than learning the task for the first time. And other things that they found in the network is that the, like, C takes two pronunciations, the letter C, depending upon the context. The soft C as in nice, where it's pronounced as sir, and the hard C, which is pronounced as ka, as in cat. So the right the so these the hard C is learned faster but saturates soon at a lower level. Soft C is learned slower but goes to higher levels of performance, right? And kids show this kind of behavior. Network also shows this kind of behavior. So it's not a deep mystery. It all depends upon the. This probably occurs because of number of hard Cs. Right? It occurs about twice as often as soft C, right? So that's all for now. And so tomorrow we'll take up these more biologically relevant studies where we compare the performance of deep networks or convolutional networks on some sensory recognition tasks, and compare the activations of the hidden layers of the network with the activations of various areas in the visual system in the brain, and show that they're surprisingly similar. There's a very strong correlations. So just to argue that even a simple deep network, which is biologically, from biological realism point of view, it's pretty bad. I mean, there is, right, the neurons that we use in deep networks are too simplistic. But even such a network is a good starting point for us to make sense out of how brain processes the stimuli, right, input stimuli, and makes these decisions. So let's stop for now and let's take it up tomorrow. Any questions? Okay, no
Sir,
questions. Yeah,
just a second. So you explained the back propagation algorithm yesterday, right?
yeah.
So how fast is it as compared to other training methods? Like you said, Hessian method is also there, right? So which one
Yeah,
is like?
Hessian is more computation intensive per iteration, but the network will converge faster. So overall training time could be even shorter compared to backprop is a first order method. It's based only on first derivative.
Okay.
Hessian based, even Hessian based ones also make some approximations for calculating Hessian. So like that they can speed up. Second order methods are powerful